Alright guys, I'm unable to be at school today. Eli got sick and had to run him to the doctor. So I want to pick up with where we were at yesterday on the chapter 12 notes and just try to run through it as quick as possible. And so what we finished off with yesterday was just because we identified that we have a correlation does not mean it's statistically significant. It doesn't mean that it's really of any relevance. And we talked about how, for example, if we had two data points, we're guaranteed that the correlation coefficient is going to be 1. But since our data set is so limited on size, that's going to have really no relevance because that could just be two data points from a population that actually has a correlation coefficient of practically 0. And so one of the ways that we test this is what's called a linear regression t-test. And just a reminder that the goal of that t-test is that we're going to reject the null. That's what we're hoping to do. Because the null is that there's no correlation, and we're trying to find evidence that there is indeed correlation between the two. So if we want to conduct a linear regression t-test on age in years versus the value of a car, and we want to check to see if it's statistically significant, then what we're going to do is on our TI-83 calculators or TI-84, we're going to run a linear regression t-test. Now I will just go ahead and show this to you guys. I already have this data inputted into my list 1 and my list 2. So then I can go to stats, over to test, up to linear regression t-test, and then my X list is list 1, Y list is list 2. I always want this to be set to not equal to 0 to do a two-tailed test, and we hit calculate. And among a bunch of other things it gives us here, the main thing is it gives us that t is -7 basically, and if we look at the p-value right here, the p-value is 0.006. And since that's less than 0.005, that means that we're going to reject the null, and the null hypothesis of a linear regression t-test is that there's no correlation. So if you reject the null, then that means that a linear regression analysis is appropriate. So what that means is we can use a straight line function to represent this data set and actually have meaning behind it. So I just stated that a linear regression analysis was appropriate. Just real quickly, I'm going to run over what linear regression analysis is. Excuse me, guys. Linear regression is the process of using the line of best fit to predict values of one given variable from another. So, and then I put here, this is useful for what's called extrapolation. And extrapolation is the process of making conclusions from given data. And instead of also saying conclusions, we could also say predictions. Right? So we're able to come up with information from the given data that's outside the range of the data set. So, for example here, the given scatter plot shows the correlation of heart rates before and after a brisk walk, along with the line of best fit equation. The line of best fit is what we're talking about when we're talking about a linear regression analysis. The linear regression is just the process of finding the line of best fit to represent this data. So, this is done on a Microsoft Excel sheet, and it gives us the equation for the line of best fit. You can see it right here. Y equals 0.847 plus 29.60, where X represents heart rate before and Y represents the heart rate after. So part A here says rewrite the equation using the variables in context of the problem. So what we can say is the Y is our heart rate after. So heart rate after can be predicted. Okay, so our previous hat notation is what we're going to use for predicted. So Y hat means the predicted Y value. So heart rate after is equal to 0.847 times the heart rate before plus 29.6. And then now we can use this equation to actually do predictions here. So it says a person who has a heart rate of 80 beats per minute should expect a heart rate of what after a brisk walk. So then we can just go in here and replace heart rate before with 80. So the predicted heart rate for after is going to be 0.847 times 80 plus 29.6. And then we just type it in the calculator. So 0.847 times 80 plus 29.6. And we get that the predicted heart rate after is 97.36 beats per minute. So we're able to use our line of best fit, which is based on the information given, to now make predictions. Whether that prediction could have been made from the data set or not, we're able to take information that was not necessarily in the data set and make a prediction using this line. So maybe that wasn't even a bad thing to point out, is that means that this point on the line is at 80, 97.4, if you will. And then it says, now looking at the second one here, a person who had a heart rate after of 80 beats per minute most likely had a heart rate of what before the walk? So in this case, it's giving us the heart rate after. So just like when we did in algebra 1 and algebra 2, we can plug that 80 in for heart rate after, and then we can solve this backward to find the heart rate before. So we're going to minus the 29.6, and then we're going to divide both sides by 0.847. Okay, so then we can just go to the calculator and do that. So 80 minus 29.6, and then take that answer and divide that answer by 0.847. And so a person who has a heart rate of 80 beats per minute after a brisk walk, based on our linear regression analysis, most likely had a heart rate of around 59.5 beats per minute before the brisk walk. Alright, so that's what we're talking about. The next thing that we're going to move into is how we use the line of best fit. And the line of best fit is also known as what's called the least squares line. So sometimes you'll see that in like your math assignments, and it's just meaning the same thing as the line of best fit. It's the linear equation for which the sum of the squares of the residuals has the least possible value. And when we say residuals, what we're just talking about is errors. Okay, so if we look here at this, if we look at our chart here, and let's say we look at, for example, 5. The point that I just created is the y hat. That's what the line's predicting should have occurred, whereas this dot below is the y value. And so in between those two is a given distance. That distance is called the error, because the line did not give us exactly what happened. The line gave us something that was a little bit off. And you can see every single data point for the entire linear regression has some amount of error. The only way it would not have any error is if what actually occurred matches the predicted, which means that it would have to be a point that falls on the line in order for there to be an error of 0. And the formula for error is just observed, O for observed minus P for predicted. And it's how far the observed outcome, which means what actually happened, falls from what's called the predicted outcome. And we can derive a little bit more, a little bit better formula, but the error formula is going to be what actually happened, the y value, minus what was predicted to happen, which is the y hat value, because the y hat corresponds to the predicted value of our line. So we can just use a graph to kind of get an idea of this right here. So this is the graph for daily pizza sales, number of pizzas sold versus the amount of sales. So it says what was the amount of sales in the day where there were 20 pizzas sold. So when we have 20 pizzas sold, and we see that the amount of sales looks to be, I don't know, I would say probably 140. So we'll say approximately $140 to $145. Let's just go with 145. That seems to be reasonable. And then on the next one it says, based on the line of best fit, what's the estimated sales for a day when 35 pizzas are sold? So the key here is it's asking us for not the Y value, but the Y hat. So if we come over here to 35 days and we follow it up, we see that the store is predicted to make between 195 and 260, right? And if we add those two, we get 455 divided by 2, which is going to be approximately $227.50. Okay, so let's just make it easy and make it an even $228. So when 35 pizzas are sold, they're expected to bring in a profit of, or make $228 worth of sales. And then it says, in the data set, what was the amount of sales on the day where 35 pizzas were sold? So we can see we have this data point up here. Well, they didn't actually, it predicted that there would be $228 in sales, but there was actually $260 in sales. So therefore, we can see that our prediction had a certain amount of error. And part D just says, what was the amount of error for the line of best fit when 35 pizzas sold? And that's where this formula comes in. Error is equal to what actually occurred minus what was predicted to occur. And we can see here, what was the amount of sales on the day where 35 pizzas sold? $260 is what actually occurred. And what was predicted to occur based on the line is $228, which means there's $32 worth of error. Okay, so the line of best fit was $32 lower than what actually happened. And then the last example down here is just if the pizza shop could sell 40 pizzas on a given day, what could they expect their total sales to be? So the fact that they're asking you for expected means we're looking for the prediction. And we can look here. If we go to 40, we don't have any actual data that happened with 40 sales. But we see that the line of best fit can be our prediction, what we expect to happen. And we see that on a day where there's 40 pizzas sold, the amount of sales is predicted to be $260. Okay? And so now we're going to just move into the linear regression equation. I have the equation here. It's y equals b0 plus b1x. Your calculators typically show it as y equals a plus bx. And we also typically think of this as y equals mx plus b. So that's kind of a little bit different notation because the calculator, what it gives you for b is going to correspond to what you typically know as the slope of the line. And what the calculator gives you as your a value is going to be your y-intercept of the line. Okay, so we're not going to run through all the crazy formula for this. We're just going to let the calculator do all the arithmetic for us. So it says find the linear regression equation for the number of years of schooling compared to the median salary example that was at the beginning of the notes. And I've already went ahead and punched this information into the calculator. You'll notice on mine, I have added this information to list 3 and list 4. So I'm going to run a test. It's going to be a linear regression t-test, but my x list is going to be not list 1, but my x list is going to be list 3, and my y list is going to be list 4. And then we'll go down here to calculate. And what you should notice is right up here at the top, it gives us y equals a plus bx at the top of the calculator. And if we scroll down, it gives us a and b. And I'm not sure if you guys can see my mouse pad right here, but it gives me a and b. It gives me a is 648.5. and B is 2050. Let's just say 2050. So then if we fill this in, we get y equals 648.5 plus 2050x. And we can then replace the y and the x with what it represents. So we can say predicted y, which in this case is salary, is $648.50 plus 2050 times years of schooling. And so we get two key things here. This 648.5 is our y-intercept, which means that with 0 years of schooling, we can expect a salary of $648.50. And once again, now that doesn't necessarily mean that that's what's going to happen, but that's just the prediction based on our equation. And then the 2050 is our slope, which means the way we would interpret that is for every 1 year increase in schooling, because it's change in y over change in x, and x is our years of schooling. So if we change this to 2050 over 1, the 1 means every 1 year increase in schooling, we can expect $2,050 increase in annual salary. Okay, so that's how we interpret the A and the B in the linear regression t-test command. That's what it represents. It gives us, not only does it give us the equation, but that's how we interpret it. The A being the y-intercept and the B being the slope of the line. Alright, and then I have another one here that just says use the linear regression t-test command on your calculator to conduct a full analysis of the number of umbrellas sold per month over the past 2 years compared to the rainfall in millimeters that month. For your full analysis, discuss the topic, the sample size, the type and strength of correlation, the result of the linear regression t-test, the equation of your least squares regression line, as well as the interpretation of B0 and B1. Alright, so that's all going to be done in the calculator with one command. So we're going to go to the calculator. And guys, once again, I put a little bit of work into this up front. I put this information, 82, 15, in February there was 92.5 millimeters of rain and 25 umbrellas sold. In May, 131.9 millimeters and 41 sold. So on and so forth. I went ahead and put that information into my list 5 and my list 6 in my calculator. So then I can just go to test, linear regression t-test, and my X list is list 5 because we're talking about rainfall predicting umbrella sales. And so my Y list is at list 6. And then I'm going to hit calculate. And we have an issue. So just give me 1 second. Let's just try that one more time. Alright guys, it took me a minute to figure it out, but I've got it cleared up here. So I've got the linear regression t-test command ran over here on the right, and you can see I've written down all the information over here. The t is 15.6, the p is 2e to the negative 13, a is negative 19, b is 0.45, s 3.58, r squared 0.9171, and r is 0.9577. And I have all this information converted over to here. So what we're talking about here is we're looking at the correlation between rainfall in millimeters of a given month compared to the umbrellas sold, let's say at some given shop during that month. We're using a sample size from the past 2 years of monthly information. So our sample size is 24 data points, or 24 ordered pairs, if you will. The type of the correlation and the strength of the correlation comes right here. The fact that R is equal to 0.9577 means that we have a very strong positive correlation between the two. Okay, so that's what we pull from that information. And then the result of the linear regression t-test is right here. We have a t-score of 15.6 with a p-value of 2 e to the negative 13, which means that our p-value is less than 0.0001, which means that we're going to reject the null. And what that means is we have statistically significant evidence that linear regression is appropriate, because we have statistically significant evidence that our correlation value is not equal to 0. Okay, so we've got statistically significant evidence that a linear regression is appropriate, and then now we bring in our linear regression equation, which is going to be y equals negative 19.1 plus 0.45x. So in terms of this would be umbrellas sold predicted is negative 19.1 plus 0.45 times rainfall measured in millimeters. Okay, so and the interpretation of that would be is if we have 0 rainfall in any given month, the business should be expected to sell negative 19 umbrellas. Now, we can't have a negative value, so typically your y-intercept doesn't really always have a meaningful interpretation. But what we do have is the slope. So the slope is change in y over change in x, which in this case is sales over millimeters of rainfall. So the interpretation of this would be for every 1 millimeter increase in rainfall, we would expect umbrella sales to increase by 0.45 units. Okay, and you could even take that up to where, make it a little bit more practical. 100 millimeters of rain should equivalent out to 45 units of increase in umbrella sales. Okay, so but we typically stick with this for every 1 unit of increase. This is what we should expect, and then people that are actually reading this knows that we can convert this and have larger applications to that. All right, and then the last thing we're going to come to with this stuff is the measures of regression. So we're trying to, with measures of regression, is we're trying to measure the accuracy of our regression. And the way we do that is we do it with a value of what's called R squared, which is the coefficient of determination. And the coefficient of determination, R squared, the coefficient of determination, denoted R squared, is the percentage of variation in the outcome that can be explained by the regression of the input variable. So that's kind of hard to understand, but if we go up here to this picture, every single one of these ordered pairs have a y value. So if we were to take all the y values and add them up and divide by how many there are, that would give us the average y value, if you will. So if we look at this line here, this would be our average y value. So, and then we're not going to do this for all the points, but we're just going to look at, say, 1 point. So this is the average y value, and which means theoretically if we were to go out and collect one data point, we would expect that one data point to have a y value that matches the average. But we notice up here we have what actually occurred is a good bit higher or a good bit greater than what the average is. So we have a little bit of variation, if you will. Okay, this distance here is called variation because this data point varied from the average. Now, in between these two here, you can see we have the predicted y value. The distance between the predicted and the average is what's called explained variation. because the line is saying, okay, we're not at the average, but I can tell you that based on the line of best fit, here's how far above the average we should be. And then anything beyond that, if this point's higher than that, which it is in this example, that's called the unexplained variation, because that line is buried even further from the average compared to what it's predicted to do. So the formula for R squared is the sum of the explained variation divided by the sum of the total variation. Now, we're not going to get into this formula. All you really need to realize is that R squared is the same as R squared such as this, which is the same thing as the correlation coefficient being squared. So with that said, if we go back to our calculator command and we look at it, you'll notice here we have R as 0.9576. I'm going to just write this down. So R is 0.9576. And we have that R squared is equal to 0.9171. Okay, they're called R and R squared for a specific reason. If I come in here and type in 0.9576 squared, you see that we get 0.917. Now, we didn't get exactly 0.9171, but that's because we rounded our decimal. So rather than being able to do the sum of the explained variances divided by the sum of the total variation, all we're going to do for this is know that we take our correlation coefficient and we square it. So if we go back up here to the umbrella cells problem, you can see that the linear regression t-test gives us the R squared value. And so it says interpret the coefficient of determination for the umbrella cells versus rainfall total. So the fact that R squared equals 0.9171, the way we would interpret that is 91.71% of the variance, or of the variation, in umbrella cells can be explained by the regression of rainfall. Okay, and that's a big statement because we're saying, okay, we're admitting that umbrella cells vary from month to month. There's a certain amount of variance in umbrella cells. But what we're saying is using the line of best fit, we can explain 91.71% of that variance. So if we were to take all these variances and compare them, we can figure out 97% of the variation, or sorry, 91.71% of the variation using this line of best fit. So that typically means that we have a pretty accurate line of best fit. Now, our lines are not going to always be 100% accurate, so just as with anything else we've done this semester, there's going to be a certain level of error. When we create predictions, we have to account for this error using what's called confidence intervals, just like what we did in the previous chapter. So we've got the standard error formula for linear regression, but we don't need this formula because for the exact same reason, if we go to our linear regression t-test, I think I've covered it up here, but we see that S is 3.58, and you can see it on the calculator here. S equals 3.58. That is the standard error. So the nice thing about standard error is, just like what we've been doing all year long, is here's our line of best fit. And if we were to think about coming in here and doing a 95% confidence interval about that line of best fit, 95% of our outcomes should be within roughly 2 standard deviations of our line of best fit. Okay, so at any point on this line, if we were to go 2 standard deviations above or 2 standard errors above or below, 95% of the observations should fall within that window. Now, we might have some outliers, some odd or some rare data. That's fine, but 95% of our data should fall in between the two. So the standard error for rainfall is 3.58. if we take 3.58 and times it by 2, we get 7.16. So for our rainfall umbrellas example, we can say 95% of the time, our regression for rainfall will predict umbrella sales within plus or minus 7.16 units. Okay, and so that's saying that we are 95% confident that we're going to make all of our predictions, the average of all our predictions will be within plus or minus 7 units of what actually happens for that given amount of rainfall. And that's a pretty big statement once again, because then that kind of relates to the accuracy of our line. So the last thing I want to do here, guys, is high school GPA versus freshman college GPA. So we're wanting to see, does my high school GPA, so that's going to be our independent variable, affect my GPA as a freshman in college? Does it seem to have a correlation? And so the first thing we're going to do is we're going to create a scatter plot. All right, and I'm going to go ahead and pause the video and do that, and then I'll bring it back in just a second. All right, guys, so I went ahead and created the scatter plot for this, for high school GPA versus college GPA. And you can see here, guys, there seems to be a positive correlation between the two. And so part B then just says to report the results of the linear regression t-test in the space below. And so I just went to the calculator and ran the linear regression t-test for that data set. So I input this data set into my list and then ran the data set. And over here, let's see, let me just rerun it real quick. So I had my data into list 7 and list 8 because I had all this pre put in for the video. But anyways, it gives me all this information. We can scroll down and look through it, but I've just recorded it over here onto the document. So as we're looking through here, guys, we've got the t-score, the p-value, the a and the b value, the standard error, the coefficient of determination, and the correlation coefficient. And so then just running through, knowing when to use what. What's the type of correlation, and is it statistically significant? The type of correlation is a moderate positive correlation, and we get that from the R value, 0.6966. The correlation is a statistically significant correlation, and we get that from the p-value. The p-value is 0.025, which is less than 0.05, which means we have evidence that it's a statistically significant correlation. And that has to happen in order for us to be able to do linear regression. So linear regression is indeed appropriate. And then what is the linear regression model and interpret? So that's our A and B. So y equals 0.43 plus 0.5x. The y in this case represents college GPA, and the x represents high school GPA. So the 0.43 doesn't have a whole lot of relevance, because what that would indicate is even a student with a high school GPA of 0, they would be expected to get a college GPA of 0.43. So that doesn't have much relevance. But what is useful is for every 1 unit increase in high school GPA, we can expect an increase of 0.65 units in college GPA. And so that's a pretty good indication that's saying that, hey, if you do better, if you perform better in high school GPA, based on the correlation, based on the linear regression, it appears that you should do well in college. So, but once again, correlation does not imply causation. So, but we still get the suggested relationship between the two with that value. The standard error is 0.3479, which is just going to give us the accuracy of the model. Doubling that gives us 0.696. So 95% of our observations of college GPA should be within 0.696 units of the prediction based on the high school GPA. And then down here at the bottom is just a few application problems. Johnny was a student who scored a 3.1 GPA in high school. What was his predicted college GPA in freshman year? So we're just going to apply this equation. We're going to apply this equation here. We're going to plug his high school GPA in, and we get that his predicted outcome is a 2.45 GPA. But it says here, Johnny finished his freshman year with a GPA of 2.0. So did the equation give us exactly what actually happened? No, it had error. We calculate that error by doing the observed minus the predicted. What actually happened was 2, and what was predicted to happen was a GPA of 2.45. So we get negative 0.45, which means the or what actually happened, was 0.545 units less than the predicted outcome. Or we could say that the predicted outcome was 0.45 units higher than the observed. Either way, saying the same thing. And then lastly here, if my high school GPA is 3.75, what's my predicted GPA for college? And so we can see the same thing here. 3.1 GPA in high school is predicted to have a college GPA of 2.45. If we increase our high school GPA to 3.75, we get a predicted college GPA of 2.87. So we have a predicted chance of doing better in college. And then right here, the last part, according to this linear regression analysis, 95% of observations should fall within how many GPA units? That's of the predicted outcome. That's 0.696. I forgot that I had that question here when I wrote up this analysis right here. So anyways, guys, that finishes up the Chapter 12 notes. Email me if you have any questions.